Hello and welcome to a new DISCUS tutorial. It's episode 3, overview on submenus. Today we are going to talk about submenus in a DISCUS read, or to be more precise in KUPLUT and DISCUS, because the DVV section is fairly complicated and not that relevant for users. That's why we'll focus in part 1 at least on KUPLUT. So what can you do to store your information in terms of how can you write files, how can you save your data to a file, and so on. These are questions we can answer. However, there's also one big submenu section in KUPLUT, which is the fit section, and I want to show that to you. So in the very end of the clip of part 1, we'll look at a macro of a square fit, and I'm going to show you how to carry that out. But first things first, what can we do to write into file or a new file? One option of creating a new file is the learn command. So if you write learn, which is indicated here in bold, somewhere into the DISCUS suite, you start the learn mode of DISCUS. That means all the input which you type in after the learn command in the new lines will be saved into a new macro file. Whenever you write ln, so for learn end, this file is created and all the input lines are stored in this file. You can later read that files and do minor additions to it and so on. This is really useful for writing a macro from scratch if you're fluent in the command language of DISCUS. However, there are also other possibilities how to write into files. One is, for instance, the fopen, fput, fclose series. This means when you want to open a file, you write fopen, fput, then allows you to add new lines into this file. You either can overwrite the file or append it to the file, so you can look at the help section to find out how that works. However, this is very useful and it can be inverted, so you can also extract lines from files, so values or variables from files. This is done with the fget command here on the right. It's also very useful, and I'll show you one example how to put at least lines into a file in a few moments. The second option how to write files or save files is the ksave command, which essentially works for KUPLUT. You use the KUPLUT save one here, for instance, for dataset one you want to save. Then you need to provide a file name to this dataset, which is here in the folder temp, known as calc dot, and then %4d stands for 4-digit long integer number in this case. So you can write variables into these file names, of course. Then you can choose your file format, which is in this case a 2-column format. So an XY file, you can also change it to a KNUPLOT file or ASCII file or something like that, and then run this block. You have also options to save pictures, so the plots you have created in KUPLUT as, for instance, a PostScript file, PNG files, or even PDFs are viable. The last thing I'm going to show you will be a fit routine. Again, a least square fit with your own equation you want to fit to your data. The equation is shown here on the right. I'm going to use, it's a phase transition kind of kinetic equation. It's really connected to the Eframi equation and describes a diameter d in dependence of the time t, how a growth or phase transition and nucleation behaves. So there are a few parameters here: d max for the maximum diameter which is reached, d0 as initial diameter, and k as rate constant. And we'll use this equation to do a fit on a dataset. In part 2 of this video, we are looking at the DISCUS level. And the DISCUS part of the DISCUS suite is huge and it has a lot of submenus. And a few of the submenus are large and really extended that we can't go through them here. And you really should look at the workshop macros or do the workshop ones that you feel familiar with those big submenus like the Fourier, the Powder, the PDF, the Patterson, or the RMC submenu in DISCUS. However, there are also smaller submenus which are really important though, which is the read, the plot, and the save, and the chemistry. That's really basic knowledge and you should go through them at least once. Again, to list a few of the other menus which are available, we can see them here, which starts with the stacking menu, so stack, which allows you essentially to layer different crystal structures on top of each other. The symmetry menu allows you to translate or to rotate your crystal structures. The domain is very important when you want to insert a crystal structure like in a host-guest complex into another crystal structure. The surface menu kind of let you shape your crystal, so you can shape it in a spherical or a ellipsoidal morphology or something like that. The decoration menu gives you the possibility to add surface functionalization to any of your structures. The connectivity goes more into the atomic structure and lets you define an environment around atoms. Molecularize let you set flags to atoms that you can work with them as a defined entity, as a molecule. Shear then lets you deform molecules or whole structures. That's also quite important. Storage is not that important. You can leave it out for now. It internally stores structures. We are going to focus today on the wave, the MMC, and the transform submenu because, well, two of them are at least quite small and we may discuss them. And a few examples will be shown here. So the wave menu is essentially one way how to create waves as they can be described with phonons. So you have transversal, longitudinal, or even density waves available in DISCUS, and we look at how to create them. These are important for like commensurate or incommensurate modulated structures. So when you have superstructures, you can easily describe them with those kinds of waves. After that, we'll introduce the MMC, the multi-energy Monte Carlo in DISCUS, which is one method to introduce disorder in a structure, whereas the energy between different types of atoms can be defined. And we can, in contrast to the RMC, which is kind of always connected to like a data set, in the MMC we have energetic types of influences, temperatures, which we can define and reduce. Then we do have the last example will be the transformation section in DISCUS. This is very important when you want to reduce the symmetry of your crystal structure, or in a subsequent step you want to use the domain submenu in DISCUS. That means that you need to adjust your coordinate system or your crystal system to another one. For instance, when you want to insert a guest molecule or guest structure into a host structure, then it's reasonable to have the same coordinates or crystal systems. Alright, with that we'll go into the macros. Okay, and here we are in the macros section. So this is the first macro we are going to execute. It's an fopen, fput, fclose series, as I've mentioned that before. So just as a short example, what is done first is that all files which are open to this point are closed, just to have a defined state. And then we start to open a file, which is called testoutput.ini. And in this file, it does already exist, but we are just going to overwrite it. And we want to print the following lines. We write fput, and the following line is hello, new cell file, and a few parameters. Within the quotation mark, everything will be written into our final file. So essentially, this whole block is written directly from this macro in the new file. Another thing you can do, of course, you can use variables in here. So the integer, real values, or strings, and you can just write them into, for example, this kind of loop. So we define a variable integer loop here. This integer goes from 1 to 8, and we just want to replace here this %2d with the integer, which is counting from 1 to 8. So when we're going to do that, and we're going to write the macro, run the macro, it writes this file. So this is our file. It writes again this nice introductory line, and then a full cell file, which can essentially be read by DISCUS again. Of course, you have to delete everything else before that. And in here, we have this kind of typical new parameter definition from the diffv, whereas here we are counting now in the loop from 1 to 8 these blocks one by one. Of course, that's one possibility to write really long files in a really short time, and this might be very useful. The second thing I want to look at next to just writing files is doing in KUPLUT. So this can be done in KUPLUT and DISCUS, but in KUPLUT we want to do the fit routine ones. So for that, I want to just introduce this kind of impediment growth model again. So you have seen the equation, the main equation, which leads to the fit of a data set, which is this data set. So at first we need to load this file. So it's essentially 2 column files with arrow values, but I just discarded them because we don't want to weigh these data points individually now. So what is given here is a scan number and the size of the particles at that time. So what is essentially done in this macro, at first this file is loaded. Then, quite optional, I have calculated a new x-axis here, so I modified the time, so from the scan number to kind of time, minutes. Then I'll go to the wait return, and then the fit macro starts. So we can go to this point, and then I defined the variables you have seen in our equation, which is dmax, d0, and k. And I have some kind of expected value. So the maximum size was 55 angstrom. The minimum size from growing was like 5 angstrom. And that were my parameters I want to put into this equation first. So my fit parameters. So what is done here now, this is the fit section. So you open the fit routine, you define your function here. So this function is identical to the function on the slide I showed you before. And then you need to give some information on the parameter. Parameter 1, P1, P2, P3. 1 here means that you want to refine the parameter, otherwise you type 0 if you want to keep it fixed. And then here is the starting value for each of those parameters. Then you can give the routine like a maximum number of cycles you want to run the refinement. You also might want to weigh the data sets if you have some outliers or something like that. And you can do some additions to it and refine the process how the fit is running. However, just for the sake of having done it here, we do that quite roughly. It also leads to a nice result. You see the C square values or the R values here are listed and how they change with time when we go on with running this macro. And then what is done here, we plot the result, and the result looks like this. I might just plot it again, that's bigger. It's not that important, however, I just want to show you what I've done here. So I've given it some title names, so this is just some cosmetic change. In blue we have essentially the data set, fluctuates a bit, but in red we have a nice fit to essentially the mean of the data, and in between, or here in green, is the difference data set. Here I just pointed some resulting values of the parameters. It's not that important, but it's a nice overview. So I really want to save the data, so I show you here how to save the data in KUPLUT. Once the fit file is essentially saved in this cryptic file name, and once the dataset is saved, and also I try to save it as PDF or PNG, so we can open that once just for the sake of having done it here. So this is our final plot of our dataset. It's not very polished, however it gives you a rough idea how the things are done. Alright, let's continue with the DISCUS macros and the submenus in DISCUS. So I wanted to show you a few, and the first one will be the wave submenu, which is demonstrated here. And for the idea of carrying it out, we should at first read a structure, which is called the Triforce structure, and I will plot it here with this section again. And you'll see now here our structure we'll work on. It's a really flat structure in C direction. So you have just one layer of atoms in the A-B plane. You have two different types of atoms. You have carbon atoms, the gray ones, and nickel atoms. And the center is displayed in green. So the idea is here now that all atoms have the same distance from each other. So what is done here is the chemistry menu. We look at the environment of atom 5 with a sphere around it. We look in the sphere of like 3 angstrom, and we find 3 atoms here, which is atom 4, 6, and 109, and the distance is always the same, 2.5 angstrom. And there are also additional information. However, the point is that CC at bonds are usually not that long, so that's why they're not displayed as a covalent bond here, whereas nickel bonds can have this kind of length. That's why you have a different representation with the lines in between the atoms here. Anyway, let's start with the wave block. So this is our wave block. We kind of want to insert here now some nice transversal waves. And essentially we put in a sinusoidal wave with some kind of amplitude, like a length of like 20 angstrom, and in 001, so in C direction, that we really nicely can see it. We'll just run that. The wave vector will be in A direction, and so when we look along A, we see in C direction we have really nice wave, and all atoms, independent of its type, form now this sinusoidal wave. And this can be also done again with longitudinal waves or density waves or whatever you want. You just need to play around with this small block a little bit. You'll get what you want to have for your superstructures and so on. What you also can do on top of that example now is to introduce disorder by an MMC. So what is done for that? So in the beginning you have to set your connectivity between the atoms which are in the structure. So these are carbon atoms, so the neighborhood of carbon and nickel are in between. distances of 2.1 and 2.55. So we have seen that the distance is 2.50. That's why it totally fits in there. We give it a random name. It doesn't really matter. Then we have our connectivity list, and then we can swap atom pairs essentially. So what we are going to do is we swap nickel with carbon to 100% of the time. And we have some, energetically driven idea here. So a target repulsive potential which is essentially defined by those kinds of energy equations. And you essentially put in the terms of energy, repulsion here. So for instance, at low R, we have really high repulsions, whereas the ideal positions for atoms are far from each other. And you can define that here. The power is 1. So just to look at the different equations which there are, and then we can choose different Jones potentials and so on. What else? Well, here I just started the calculation because the calculation time is rather medium high. So we have 500 cycles of feedback after like 50 moves, and the temperature of 2. So the higher the values really are here, the longer the calculation will take. And that's why you should always apply high values with respect to the number of atoms you have. So a multiple of the number of atoms you have in your structure. Just for the reason of having done fast, and we see still some kind of result. We see essentially the result here. So you can see that carbon and nickel swap positions some places. However, still the kind of now diffuse inner triangle is visible. However, the higher the values of these cycle numbers of moves will be, of course, the more diffuse the inner triangle become, and at some point it's fully disordered, and you won't differentiate anything in this plane anymore, in this wavy plane. Okay, having said that, we can go to the second macro, which is the transformation macro. Essentially, the idea here is to transform one system to another system in terms of like here coordinate system. So the idea is we have an hexagonal cell which looks like this. We have here our cell file. It has a gamma parameter of 120 degrees. So this is typical for hexagonal type of cells. And we want to transform in an orthorhombic cell. That means that all of the angles are 90 degrees, and the other cell parameters can different. However, how we want to do that? So at first, of our targeted coordinate system, we have to save our values. So we essentially need to calculate the transformation matrix between the two coordinate systems. So what we do is we save those targeted cell parameters and angles, for instance, and then we try to calculate. So we read the real or the current structure we want to transform, and calculate from the fraction of that the new factors for like the position of the coordinates, so that we can calculate the new x, y, z values of the coordinates. That is essentially what is done here. Another thing is that if I just show you the structure once of the hexagonal cell, which is this plot here, then again we see a typical hexagonal cell. It's stacked, so we have a stacking direction here in C direction, the very long C direction, and in between, so the gamma angle is around 120 degrees, and we again want to put that to a 90-degree angle and swap the stacking direction from the C direction to the B direction, because in an orthorhombic system, usually by definition, this B value needs to be the highest, and that's why we need to swap this value to the position essentially here. So what essentially is done is you calculate the fractions between those B and C coordinate values. You calculate here a rotation matrix. You save the values of this 90 degree is essentially a 90-degree rotation here. In here, the output of these symmetry submenu is kind of put out in rest values. You can save them into different real variables, and then you can essentially calculate the transformation matrix, or this new line which carries the rotational information, so that you can swap the C with the B axis. And here you're essentially in the new, so this is in the transformation module and submenu. There you can have the new fraction which you multiply the atom XYZ positions with. We do no origin shift here and run it, and the result of that we do here show metric will be that the new cell is 2.8, 12, 3.6. So again, the B value is now the highest, and we have created the beta now with 90 degrees. So what we have done is we have put the structure in now an orthorhombic crystal or coordinate system, and we will just plot it once with this kind of section in the macro. And you see now here the coordinate system is a 90-degree angle everywhere. The stacking direction is along B, and we really put the same structure now into this new coordinate system. And yeah, the use of it is essentially when you want to use the domain menu afterwards or something like that, so you want to insert structures in other structures and modify it that way, so you can still do other modifications now, like rotations and so on. It's really dependent on what you want to do next, but this is in general how to, for example, symmetry reduce structures or transform unit cells. Alright, with that I want to end here. So the next videos will also be about some in-chain and consecutive types of submenus in DISCUS. With that, see you soon.